This one in particular, it's at a beautiful venue. Pretty much everybody's staying in the hotel here. And so that means, after the sessions, people are going out and getting a beer and continuing the conversation. And it's just a great way to experience the conference.
All right. Yeah, we're mic'd up. I guess let's get started. So let's start it off with what you should expect to learn from this talk. We're going to get on the same page about what a units library is and what you really gain from it. We'll talk about some traps and pitfalls and some of the interfaces that can protect against them. We're going to share some practical strategies for how to go from no units to units. There's good news here. Finally, we'll get into the nitty-gritty for some specific design questions you're likely to encounter while interfacing with linear algebra libraries and other languages. Okay, so who am I? My name's Chip, and I work at Aurora Innovation. Our mission is to bring the benefits of self-driving safely, quickly, and broadly. Among other things, I'm the lead designer and maintainer of our units library. This is actually the second units library that I've helped build in the autonomous vehicle space. I was also the lead designer for the one at Uber's Advanced Technologies. I'm going to use our units library as a case study to illustrate the ideas in this talk. Now, why not use an open source library? A couple of reasons. First, this talk is about units libraries generally, not one specific library. You should be able to apply the concepts that you learn to whatever library you use. Second, this library is a second-generation library which was designed around the principles and insights we'll go over in the talk, and thus it illustrates them the most naturally. Some of you may know there's a new units library, MP Units, which is making a concerted push to become the standard units library. We support this effort, and we both hope and expect that it will succeed. Fingers crossed for C++26. We're actively engaged with the authors to do whatever we can to help STID Units become the best library that it can be. So, what are we talking about? Let's start with an example of the kind of code we used to see all the time. We got a sleep function which takes a duration, and it helpfully labels the units for that duration as milliseconds. But when we read a call site in a random part of the codebase, it just says sleep 1000. 1000 what? This kind of interface is a bug waiting to happen, and it typically doesn't wait very patiently. Here's what we would do now. We'd use STID chronotypes in our interfaces. Why? Well, for one thing, the call sites are now perfectly clear. We can see the units directly. For another, they're more flexible. We can pass something like 1 second and we'll automatically get a correct conversion. And finally, they're safe. If we pass something like 1 million microseconds, it won't compile because microseconds to milliseconds is a lossy conversion. A decade ago, the Chrono library taught us that we can have nice things, and now we all refuse to settle for anything less. Unless we're dealing with any dimension other than time. Well, we all know the pain points for time units. Do we ever really see problems from any more obscure dimension, like, say, impulse? This is by now a familiar tale to many, but on September 23rd, 1999, the Mars Climate Orbiter lost communication with Earth. NASA software received impulse values which it interpreted in units of Newton seconds. Lockheed software produced impulse values in units of pound-force seconds, which are different by a factor of about 4.5. Now, a lot of things had to go wrong in order to lose the spacecraft, including significant organizational issues. But it's still true that if they had had a units library and used it correctly, then the error that brought down the spacecraft could not have occurred. So, is that why we should use units libraries? To prevent unit errors? The truth is a little more subtle than that. But first off, do they prevent this kind of error? Yeah, they do. But is this the main benefit that they bring? Not really. It turns out that in practice, unit errors are extremely rare, at least everywhere that I've worked. Change all your numeric types to solve a problem that almost never happens. Just maybe not the most compelling sales pitch. Why are they rare? Because developers do significant manual work to maintain unit correctness. Here are some rules that people typically follow to achieve this. Every identifier which holds a quantity must end in a suffix which indicates the units. Stick to a single system of units, typically SI, everywhere. If your quantity is in some other units, you convert it right away. And this is fine. Assuming you have a strong culture of code review, culture of unit tests, integration tests, end-to-end tests, this is effective at preventing almost all unit errors. It's just that, wow, is it a lot of manual work. And yet, if you think about it, there's nothing wrong with the binary executable. The numeric types that flow through the program, the double, float, int, they're exactly the same types that we want flowing through it. This is the key point of what we want from a units library. We want different source code which produces the same program when we get it right, but does not build when we get it wrong. Now, the usual case is that the code is correct. We passed the right values to the right places, got the right bits flowing through the system. So what value is the units library providing in this usual case where we end up with the same program that we would have had anyway? It's not the machine side, it's the human side. Interfaces should be easy to use correctly and hard to use incorrectly. It's the fundamental rule of software engineering. It's what keeps the software easy to change without fear. A units library shouldn't feel like a nitpicking nanny ready to whack you over the head with compiler errors the second you misbehave. Rather, it should feel liberating and accelerating, like having a trusted assistant who understands what you mean and always gets the small stuff right. With a good units library, you move faster. You can build more expressive, next-level interfaces, avoid mixing up parameters, have concise yet readable call sites, reduce your cognitive load by reasoning more locally about your code, and, yes, it does eliminate an entire category of error with no runtime penalty, too. So, now let's see how we might build an actual library. We'll start with a crash course in quantity calculus to get us all on the same page about what we're actually building. Then we'll build up our C++ library in conceptual layers so we can see how units, quantities, and dimensions all fit together. To start, a quantity is something that is measured, like the distance between 2 points or the temperature change in a pot of water. To actually perform this measurement, you need a unit, which is just some other quantity that we can use as a reference. So here's another distance which we've singled out and called the foot. We can see that if we stack two of these end to end, it gives us the same distance as the first one. So this quantity equals 2 feet. 2 is the value, feet is the unit. Of course, we could use another unit, say the inch. If we measured the same length using this unit, we'd find it took 24 of them end to end. So this value is 24. Importantly, this is the same quantity. That is, if A is 24 inches and B is 2 feet, then A equals B. It doesn't equal like 12B or something. Now, a dimension is basically a collection of quantities that can be meaningfully compared, an equivalence class, if you will. You can compare a meter to a yard. Turns out the meter is a little bit bigger, so they have the same dimension. But it makes no sense to ask if a meter is bigger than a kilogram. They have different dimensions. All right, quantity calculus is deep. But this is a crash course in a software talk, so just follow this simple rule. Treat unit symbols like algebraic variables. Suppose we have 2 units of the same dimension. One is x, and one is equivalent to 12x. Maybe they're inches and feet again. The square brackets here in these slides are going to be our notation for indicating the unit of measure. So to perform this operation, we first choose a common unit of that dimension. Let's say we choose x. Then, after converting everything to x units, we can just add the values. Now, take another unit y, which has a different dimension than x. In this case, trying to add these quantities is meaningless. But remember, we can do algebra with quantities. So, if you have an x per y unit, you can multiply by that, bringing everything into x units, and then you can simply add. Finally, all right. Finally, you can always take products and rational powers of units. Stop talking.
Yes, 1 second. All right.
Okay. Yeah, I can hear myself, which I usually can, but I can hear myself louder. All right. If we look at this slide, yeah, we can always take products and rational powers of units. If we look at this slide, we can see what we need from our unit representation in software. We must be able to change the magnitude of a unit to scale it. We must be able to distinguish between incompatible dimensions, and we must support products and rational powers of units. And we have to be able to support reasoning with that too. So we have to know that a y times an x per y gives you an x, and that you can add that to any other x. Okay, so here's our strategy. We're going to build our unit representation from 2 key parts. The dimension will be what distinguishes different kinds of quantities, and the magnitude, which is a positive real number, gives us the relative size of units of that dimension. So inches and feet both have a dimension of length, and whatever the magnitude of an inch is, we know that the magnitude of a foot is 12 times bigger. If we want computable relationships between units, so that we know that a speed times a time is a length, we're going to need to do some template metaprogramming. But don't fret. We place the utmost importance on the end user experience. If we're doing this right, none of the template metaprogramming leaks out to the end users. They will use templates, but nothing they see will be any scarier than the int in std vector of int. That said, let's see how to make some dimensions. The common approach is to use a type list of powers of base dimensions, length, mass, time, etc. We can represent other dimensions as products and powers of these base dimensions. For example, acceleration is going to be just length divided by time squared. We're going to look here at the product operation. To carry it out, we're going to end up just merging the type lists. But in order to be able to merge them, we need a well-defined ordering of the base dimensions. In this example, we're going to choose the ordering length, mass, time, then angle. If you're curious, the way that we instantiate this ordering is with traits on the base dimensions. Okay, now let's briefly step through this multiplication operation to see how the merging works. At the head of our lists, we have a length and a time. These are different. Well, length comes first in our ordering, so we're going to copy it directly to the output. Now we have time and time. These are the same, so we just add the exponents and copy the result to our output. Finally, angle and angle. Again, the same. But this time, when we add the exponents, we get 0. Therefore, we omit angle from the output so that we keep our types unique. In the end, we find that the product is length to the 1 times to the -1 for the dimension. So this is the products operation. I'm skipping over the power operation, but we do provide that too. And once we have those, we automatically get inverse and quotient and root too. That was dimension. We also need a representation for the other half of our unit, which is magnitude. People often use ratio here, but surprisingly, we actually use the same representation. Just instead of basis dimensions like length and time, we have basis numbers. It kills me to not have time to talk about this, but if you're curious about how to represent positive real numbers by a vector space over the rationals, let's chat later. Last thing to note in passing is that magnitude also has product and powers, and therefore also inverse, quotient, and root. And now we can build our unit. All the hard work is done already. We just delegated it to the dimension and the magnitude. So to compute the product of a bunch of units, you take the product of their dimensions and the product of their magnitudes. And it's the same thing for all the other operations. Nice and easy. Okay, finally, having built our unit machinery, we're ready to define some actual units. We're going to start by choosing one unit for each base dimension. It honestly couldn't matter less which one we pick. We can also define templates for various prefixes like the SI prefixes to make it really easy to build new units on the fly. So a centi-U is just a U scaled by a factor of 1/100th. We can make even more scaled units by arbitrary scaling factors. For example, an inch is 2.54 centimeters, which we can instantiate like so. And this is going to give us a path to get things like miles from inches and hours from seconds. And finally, we can build up compound units by taking products of powers of existing units. That's cleaner than using raw dimensions and magnitudes. It speaks the truth more directly. Really, we should only be directly defining 1 unit per base dimension. Now, I want to emphasize that these unit types have nothing to do with values or numeric representations. The product of newtons and meters is joules, regardless of whether we're using int or double or whatever. In order to store values, we need to go the next level up to quantity. Now, we already have a very familiar example of a kind of quantity type. It's did chrono duration. Here's the correspondence. A duration is templated on a rep, which is the underlying numeric type, and a period, which indicates the duration unit. So what this would look like as a quantity is quantity of the duration unit with this period and the rep. So what we're doing here is just making it explicit that our unit of measure has the time dimension. And now it becomes quite clear. With a general quantity, we could just put any unit in that slot. Now let's see how to get values in and out across the library boundary. We're going to use a quantity of meters with a double rep for all of these examples. Remember that we want the same data flowing through our binary as before, double, float, whatever. So we have the make quantity helper. You name the unit, and it deduces the rep based on whatever you pass it. And this is nice because it makes the unit feel like a tag. It feels like a sort of semantic annotation. So this is quite powerful and flexible. It's also a little bit verbose. We don't want to overburden our users. So we also provide name functions for our common units, such as this meters function here. Just like make quantity, it's going to wrap and deduce whatever type you pass it. There's a third way to create a quantity if you happen to have a literal. No surprise here, it is a user-defined literal, although this is going to only work with int and double types. Now, notice what all 3 of these have in common. You have to specify the unit at the call site. What's missing from this is we don't provide a public constructor for quantity, and that's intentional. We're going to talk a bit more about that when we get to the concept of unit safety. As for getting values out of the library, you're going to use the .in helper with your unit. So for a variable length, you'd say length.in meters, which gives you the length in meters. Notice that the unit name is like a kind of password that you set when storing the value. To retrieve the same value, you must speak the same password. And we see that every method listed here visibly indicates the unit meters in some way, and you can't cross the library boundary in either direction without naming the unit at the call site. We'll talk more about this in a bit, but for now, just note the clarity that it provides at the call site. Okay, of course, just putting values in, getting them out, not very exciting. What can you do with these quantities? Well, we already know it's always valid to multiply and divide them and raise them to rational powers. Let's consider an operation that might not always be valid, say addition. We can add 2 quantities of the same unit, no problem. And that's true even if we had to do some reasoning to get the unit. So 2 meters per second times 3 seconds gives us 6 meters, which we can then add to the other quantity of meters. Cool. What we definitely can't do is add incompatible quantities. So 1 meter plus 1 second, that's just a mistake. And this is always going to be a build error. Then there's something like this. 1 meter plus 1 foot. Is this meaningful? Should the library accept this? Yeah. I mean, thinking in quantities, this totally makes sense. This is a well-defined quantity of length. But thinking in code, we can't carry out addition until we first get the inputs into a common unit. So This is going to take us to the next level of the units library, which is conversions. Let's take this practical example. If you're driving at 60 miles per hour for 10 seconds, how far do you go? Well, the value is 600, 60 times 10, and the charming unit is mileseconds per hour, which sounds weird, but really it's just 1/3600th of a mile. Okay, cool. Now try assigning it to a quantity of meters. Some libraries look at this and say, whoa, the units don't match up. If you want a conversion, you've got to ask for it, maybe with some kind of quantity cast, which we here spell .as. Everything is explicit. So Boost Units, for example, takes this approach. Other libraries say, look, we know the exact conversion factor between this weird unit and the target unit meters. We know it at compile time. Let's just multiply by that ratio. MP Units takes this approach, as do we. We'll look more later at some of the trade-offs involved in this choice. There's also room for a kind of a top level here. How will your project interface with the units library? This is conceptually distinct from the library proper, and it can have a big impact on that last 5 to 10% of user experience. Suppose your project starts from the typical manual approach where you have a preferred unit for each dimension. Well, then you can just encode that preferred unit in your main library types with these dimension named aliases. Now, these are nice because most end users don't really care about the unit, nor in many cases should they. What they should care about is the kind of thing they are passing, the length of the car, the speed limit. So, dimension named aliases can be one way to promote flow when reading the code. What's more, if you're using the same default unit for most cases, you're going to reduce the number of conversions, which should be nice. And remember, the times that people actually do care about the unit, they can still use quantity. It's still there. Another really important consideration for the end user experience is to be fanatical about minimizing the number of headers they have to include, ideally getting it down to 1. So for example, if you include units, you should get all of your math and utility functions for free, sine, arctan, round. Asking people to change their fundamental numerical types is already an uphill battle. So let's not make it even harder by making them guess which header they forgot when their code doesn't build. All right, let's now step back, look at the big picture of what we've just seen of the library's structure and interfaces. The foundation is units and the ability to reason about units, products, powers, prefixes, and a whole bunch of commonly used units provided out of the box. Again, this level is independent of the values. For that, we need level 1, which is quantities, the ability to tag arbitrary numeric values with a unit. We can multiply or divide quantities, and for same type quantities, same unit, we can add, compare, and assign them. As for making a quantity, we have a few ways. The make quantity helper is verbose but flexible. Something like meters is more succinct, and _m is great when you have a literal. Notice again that you cannot enter the library without naming your unit at the call site. To get values out, you speak the same password you set on entry, .in meters. Again, you must name the unit at the call site. In fact, this API is awfully suggestive. And as we move to level 2 conversions, you might have guessed what's coming next in this interface. You can, in fact, pass any unit to .in, and it will perform the conversion if it exists. We can see that this usage of .in, just like the other one, is going to exit the library. If you want to do a conversion but keep it as a quantity type, then you call .as. So .as has the same syntax as .in, so it makes the library easy to learn. .as is our quantity cast, and .in is our value extraction. So these APIs lead to nice, readable, learnable, concise, clear call sites. Okay. We also saw there's this kind of optional part to layer 2, which is the implicit conversions. This can reduce friction for mixed unit comparison, addition, etc. Though there are some trade-offs here that we're going to get into, and not every library permits this part. Finally, there's this optional sort of top-level layer that you can put on the library to tailor it for your project. So, lots of design choices here. What are the principles that should guide our decisions? We're going to look at the main ones that have guided the Aurora units library. The point here is not everyone should go do things exactly how we've done them. Rather, it's these have worked well for us, and let's have them be discussion points for everyone else. So like, it's okay to make a different decision, but what we want to prevent is people not consciously making a decision because they didn't know what to consider. First off, batteries included. We really want our quantity types to be at least as capable as the raw numeric types that they wrap, and ideally more capable. So if someone takes the raw value out of the library, we see that as a clue. It means we didn't meet their needs. And then we always ask, can we fix that? Here are some examples. So you'll see streaming the value of the angle in degrees and then manually streaming deg. Taking the sine of the value of the angle in radians. Getting the value out in degrees, normalizing to 360, and then putting it back in. Okay. In every case, these are things the library should support. In fact, with native support, these things end up better than what you could get with the raw numeric types. You can get your units printed for free. You can actually write sine of 45 degrees. And you can take the mod via 360 degrees. Or better yet, and take the mod via one revolution. That's the idea you're really trying to express anyway. Units libraries are all about better user experiences, not burdening users. Next up, wrapped types mimic unwrapped types. We want people to be able to leverage their well-honed C++ intuition. It's got to be easy to mix and match types for the rep. So we know that a float times an int is a float, for example. Well, if you have a float times a wrapped int, it should be a wrapped float with that same unit. And if both inputs are wrapped, the result should have the same rep end value as before, wrapped with the unit that results from the computation. The units should sit on top at build time and get out of the way at runtime. Next up, quick to compile. Every units library increases compile time because you're doing work that you weren't doing before to produce the same binary executable. It is critical to minimize this burden, and to minimize it, we must measure it. We keep some scripts handy so that we can measure compile time changes at the drop of a hat. This plot shows some quantity-heavy files with and without the units. We can see that the cost is measurable but not subjectively noticeable, and I think that's a really good way to frame it. Because subjectively noticeable is about where you start losing users. There's another units library we tried where just when you pound include it, you can feel the difference, multiple seconds per target. I saw different teams across multiple different companies choose not to use that units library for that reason. So compile time performance matters a lot when it becomes bad enough to notice. Finally, let's talk about unit safety. This principle is all about readability, increasing confidence and reducing cognitive load. How can you judge whether a line of code has handled units correctly? For quantity types, we know that the units library takes care of this. So we look at the boundaries, the places where values enter and exit the library. Cognitive load depends on how far you have to look to make sure those values have the right units. The best possible case is that you don't have to leave this line of code. To see what we mean by this, we'll start with an example of code that is correct, but is not unit safe. We got some protobuf message definition. Now, if you're not familiar with protobuf, that's fine. Just ignore the equals 1 and 2 and think of this as a serializable struct with two members, length and width. So this line here, this C++ line, does not have unit safety. Yes, the units of rect.length are indeed meters, but to know that, you have to look up some other file and go read a comment. Not so good. In fact, no feature of any possible units library could make this line unit safe. The root of the problem was the name of the protobuf field. Using only a comment for the units has poor call site readability. We know how to handle this correctly. We just add the unit suffix. Now the code is unit safe because we have a proper handoff of the units tracking, from the suffix on the raw number to the name of the function that makes the quantity. We call meters, and we pass it a length in meters. Could there still be a units error? Yeah, we could have initialized the field with a length value measured in some other unit. But if there is an error, and this is the point, then it's in some other line, and we can see it in that line. This line is correct by inspection. We can read it. We can move on. So, we want our interfaces to be as smooth and as user-friendly as possible. But what we really don't want is for wrong code to look right. Let's talk about some of the ways that can happen and the strategies that we use to guard against that. Remember we said some libraries don't want those level 2 conversions to be implicit? The reason is that it can hide computations you don't expect, which means you can unwittingly take on risks. Consider, you can compare an integer number of meters to an integer number of yards, and you can get the correct answer. How does that work under the hood exactly? Well, we convert the values to their common unit, which is going to be the largest unit that evenly divides both. Now, in this case, we don't have a special name for this unit, but it turns out to be just under a millimeter. Let's call it a U. So a meter is 1,250 U's, and a yard is only 1,143. Now the point is, the code makes it look like we're comparing 11 and 12, but the implementation is really comparing two 5-digit numbers. The possibility for surprising overflow is now clear. Does this mean we should forbid implicit conversions? Well, let's look at some example conversions using an integer quantity of meters as our starting point. We're going to find the failures we see fall into several different categories to consider. First, .in meters itself, that's pretty easy. You always get the same value out. This always works, full stop. Millimeters, that's interesting. There's always a right answer that's an integer, but we've just seen that we can overflow. Users who are spoiled by the chrono library will expect this to work, but the way the chrono library avoids overflow is by making all their user-facing API types 64-bit. We want to encourage arbitrary types, so we need to be careful here. We'll explain the approach we took in a minute. First, let's continue on with the landscape. Next is length.in feet. This is physically meaningful, but for an integer number of meters, it's almost never an integer answer. So this is an easy one. We just forbid it, as long as the destination is an integer. Now the last one is the easiest of all, length.in kelvins. This doesn't even make physical sense, so we're going to forbid it always. But that said, that's the only one here that doesn't make physical sense. Okay? All the others are conceptually meaningful, and so there should be some way to support them. And there is. The way that we do this is to let users provide the desired rep as an explicit second template parameter. We teach people to read this like a static cast. It's a sign to the reader that, yeah, this could lose precision or could overflow, but I am forcing the type I want. Of course, just as with the chrono library, the intermediate computations take place in the widest appropriate type. So you don't have to worry that, say, 1 meter.in feet double will give you 3.0. It's going to give you 3.28 and change. Okay. Now we're ready to talk about how we think about the overflow problem. Since the 2-argument version is semantically a static cast, we tell people to strongly prefer the unit-only version, because this gives us a place in our APIs where we can hang a safety net. Here's the implementation of that single argument version. If we got here, it means that the caller has said, please convert to this unit, but only if it is safe to do so. We implement that safety check with this policy trait class, implicit rep permitted. It depends on the rep that you're using and the specific unit conversion. If we pass that safety check, we just delegate to the 2-argument version. Easy. Now let's take a peek at that policy. So here's the rough idea, transpiled to slide++. Let's unpack this a bit. First, we see the familiar chrono duration policy hiding here, which gives that library such usability and expressiveness. We permit automatic conversions if we're storing the result in a floating point type, or if we're simply multiplying by an integer. Now that last part we've seen is where we're running the risk of overflow. So what we do is to make an adaptive modification. For every type, there is some smallest value that would overflow. What we do is to check what that overflow threshold is for this conversion. If it's small enough to be scary, we forbid the conversion. We picked 1,000. Why 1,000? Because people tend to choose units that are suitable for their problem. If their values tended to be bigger than this, they'd use the next biggest SI prefix, say kilometers instead of meters. This creates a kind of policy surface across the numeric types where we adapt to the level of overflow risk actually present. And by the way, this policy isn't just for end users. We use it in our implementations as well. So all those easy breezy mixed unit operations, addition, equality, they automatically respect the policy surface too. So we have this little helper here, using common type, that performs any operation on two objects by first casting them to their common type, but only if we think it's safe. And how do we check that? Just as we said, we use the single argument version, which opts into that safety policy. And then the implementations, of course, they're going to just call out to that helper, and so they opt in as well. Now, the point of all this is not that 1,000 is the magic number where you stop worrying about overflow. I'd say that's very debatable. Rather, the point is that if you want to tag arbitrary types with units, but you also want to deliver the usability that people are rightly conditioned to expect, an adaptive policy is one way to thread that needle. Here's another pitfall caused by our liberal support for different numeric types. Car going 65 miles per hour. How many seconds does it take to cover a 60-meter distance? Picture the scenario physically. It's perfectly meaningful. So the library had better get it right. And it does. We compute the duration and express it in seconds, and we get a value of 2 and change. Now let's look at an innocuous change. What if our literals are integral rather than double? With our units goggles on, this still looks fine. We're still going to correctly compute the duration, and we're still going to express it in seconds. Of course, we realize these are ints, so we might expect an even 2 rather than 2.06. But with our C++ goggles on, we spot a real problem here. Wrapped types mimic unwrapped types. The value that we compute is 60 integer divide 65. That happens first. Only then do we convert from our charming little unit to seconds. See where this is going? We're going to end up with a 0 instead of a 2. That's a far bigger error than a standard truncation error. And this is really obnoxious because wrong code should look wrong. But this code looks almost exactly like this code. It looks right. Now, this is C++. We can't forbid people from shooting themselves in the foot. But we can put a safety catch on the foot gun. So for integer division, the way we handle this is we force people to spell out integer quotient. You want to mix unit conversions with integer division, you better at least alert your reader first. Okay. Suppose this all looks great and we're ready to convert our code base to a units library. Question, how does one do that? Well, we have some very good news here. Incrementally, as desired, using a units library is not an all or nothing proposition. Using that principle of unit safety, we can play nicely with legacy code that still uses human readers to keep track of the units. Let's take a peek at some of the key moving parts that we're going to encounter and see how they all fit together. First off, we've got free functions. So here's a pretty standard kinematic function with raw numeric variables and unit suffixes. The strategy here is to insert a shim. You are literally just adding lines, not changing them, which gives a nice readable diff view as well. So here's the old text. And here's the text we insert, the stuff that's going to show up in green on your pull request. We slide the new API in there, and then just below it, we slide a simple comment that says, type unsafe shim for the above, deprecated. All new code should use the new API, but we don't have to run out right away and change all the old code everywhere. No megadiffs. And once we've migrated everyone over, we can just delete the shim. On the implementation side, here's where we started. The first thing we do is to make a copy and update the code. Notice we already get a little bit of a nice cleanup. The unit suffixes go away. And now we turn our old function into the shim. This part is completely mechanical. You transfer each parameter into the units library using a unit-safe handoff, and you transfer the end result out of the units library using a unit-safe handoff. So for example, meters per second of speed MPS on the input. And then on the return type, the function stopping distance underscore m returns stopping distance dot in meters. Okay, now for member APIs. These ones actually benefit really nicely from our old manual approach to unit safety, where we needed to add the unit suffix to all of our names. If we're now returning a strong type, that unit suffix would either be redundant or wrong. So the new version loses the suffix, which gives it a different name, which means that these members can peacefully coexist indefinitely as we work to upgrade callers one at a time and at our leisure. And in the glorious future, when all callers have been migrated, we can just delete the old versions. Now, all of this assumes that you were keeping track of units before, and you didn't have something like double length. In fact, my whole thesis that unit errors are rare assumes that you are doing this. This has been true everywhere I've ever worked. If it's not true for you, well, it's kind of time to pay the piper. You have options, but none of them are very appealing. But you do need to start tracking your units before you end up with your own version of a Mars Climate Orbiter event. All right, now down to the level of implementations. We can upgrade our code base one function implementation at a time. And the way that you add type safety to a type unsafe line of unit safe code is to name the type, like so. At this point, you have already achieved unit safety. By storing your result in this type, you know that if your program were wrong, the compiler would tell you. It is, so it does. So now we go about the mechanical and straightforward process of fixing the error. Every individual change is unit safe. It's a visibly correct handoff of the unit information. Once we've checked this line and it builds, we don't need to worry about it again. Unit safety means verifying correctness in a single line of code. Now, granted, this is more clunky and cluttered than what we started with, but it also isn't the end of the story. Remember that at the same time, we're upgrading our other interfaces incrementally to use the unit's types. Once we do so, we end up with code like this, which is both simpler and safer than what we started with. And of course, if we had upgraded those interfaces first, we could have skipped directly to this last phase. The point of showing the ugly intermediate step is just to say you're not blocked on that. You can go as you like. Okay. Switching gears now, it's very common to want your units library to play nice with vectors and matrices. We're going to use the eigen library as a kind of case study and look at two big picture strategies and show you the trade-offs inherent in choosing between them. First approach, probably the most natural. We can have an eigenvector 3 of double float. Why not a velocity? And yeah, you can indeed use a quantity as your scalar type. So this lets you write nice, readable statements like r equals r naught plus v times t, and you'll still get all the benefits of your unit checking. The thing is, though, this doesn't quite work out of the box. You need to teach eigen how to support operations with your scalars. So they provide these traits which you can specialize for your types. And what this means here is, given input types A and B and a binary operation op, you tell eigen the return type of A op B. Here's one case you must provide. A and B are both the same quantity type. Let's call it a T. And the binary application is multiplication. So what is the type of T times a T? It's literally just whatever the type of T times T is. Okay? This might seem a little weird. Like, why did we have to tell eigen that the type of T times T is whatever the type of T times T is? Like, what did it think it was? Well, it thought a T times a T was a T. And this makes great C++ sense. And it is irreconcilably at odds with the fundamental defining properties of a dimensioned quantity. A length times a length is an area, not a length. Now, assumptions like T times T gives T are so deeply woven into the fabric of the library that even specializing the traits which eigen provides is not enough. Back at ATG, we did find some operations that wouldn't work unless you even would patch eigensource. But there's good news. Turns out that this whole approach is misguided anyway, and the eigenlibrary is actually fine how it is. There's another strategy, which not only avoids ever needing to patch eigen, not only avoids ever messing around with those trait specializations, but it lets you fulfill real-world use cases which would be inconceivable with the approach that we just saw. Consider a 2D pose, which describes all the ways that a rigid body could be situated in a 2D space. You've got a position with 2 degrees of freedom and an orientation with 1, so 3 degrees of freedom in total. And this means we can describe movement in this 2D real space with a 3-dimensional abstract vector space. If you're curious about what these vectors actually mean, the term to Google here is a Lie algebra, L-I-E. Now, these vectors, though, they do have units, and the units are meters and radians. So this is an eigenvector of what exactly? Well, it can't be an eigenvector of anything. But remember, the bits are all right. We want the same types flowing through our executable, not just double, but eigenvector of double as well. We want the units to sit on top, just checking correctness and making code more readable. So, what do we need here? First, we need some kind of unit-aware wrapper, which is this vector 3dt alias. 3 for 3 dimensions, d for double. Second, we're going to need some kind of unit provider, where we can index into it and get the units for that index. Now, that unit provider might sound like kind of a nightmare. We frequently use 6x6 matrices. These have 36 entries, each of which has its own units. Are we going to need up to 36 different template parameters? Surprisingly, no. It turns out to be extremely simple. For every useful matrix, the units must be factorizable, meaning they can be expressed as the product of a row unit and a column unit. And it gets better. When you do a matrix product, the column units of the first matrix and the row units of the second matrix go away. They collapse down into a single unit, which we can fold into the row units of the result by multiplication. Let's see how that looks for a simple example. The entries of these matrices and vectors are the units, not the values. I've shown the row units in blue and the column units in green. Every matrix entry's units is the product of its row unit and column unit. And now we'll zoom in on one instance of the multiplication to see how that works. I've color-coded the elements that participate together. We can see that every partial product produces the same unit, which is rad. So that's how units work in matrices. How's that look in code? Here's an example unit provider using a unit provider 2D template, which we will typically give a meaningful alias. Here we've used my units, very meaningful, and that's going to keep the end user call sites more concise and readable. An example of this might be SE3 units, for example, in real code. The provider itself takes 2 template parameters, one for the row units, one for the column units, and we can index into it. So meters times radians per meter is radians. Meters times hertz, well, that's just meter per second, etc., etc., etc. So this is how we can make the unit provider part. Now for our matrix type. We can make our quantity matrix the same way that we made quantity. It's a template based on the units and the underlying type, which is now a matrix. Now, we have to define our operations, and there's a bunch of them, but we're just going to use one as an example. This one is multiplication with another quantity matrix. On the implementation side, 2 parts to notice. First, our output units will be the product of the input units. And by product, we mean just what we saw before, where you collapse and fold the inner units and you retain the outer ones. Importantly, if this product is ill-defined, the program will not build. And then, Having done that, having passed that check, we just return the matrix product of the raw numeric types, pure unadulterated eigen under the hood. Although, in fact, I never actually mentioned eigen at all. And this approach doesn't know that you passed it an eigen matrix. And that's really nice because you won't always be passing it a matrix. Eigen is fast because it's smart. When you tell it to multiply or add matrices, it doesn't rush out and do the work. Instead, it creates a lightweight proxy object which remembers what work to do. Only once it knows the full computation will it perform it in the most efficient way. So here's a benchmark that we use to test our proof of concept. We run it under two strategies, raw numeric matrices and units. We start off by getting the appropriate kind of inputs for our strategy. A is a matrix, dt is a scalar, and they will have units or not as appropriate. And then what we do is we take this horrible computation and we run it in a benchmark loop. Even though we never had to explicitly create a wrapper for eigen's proxy types, we measured the same performance for both strategies, which means that this approach can scale. Now, I have elided significant implementation details. This is just the slide++ version, but the gist is there. The thing that appears simple and natural is in fact a bit of a trap. There's a hard cap on the kinds of things you can support, and it's a lot harder to get working than you would think. Units on eigen, this second strategy, lets you write one wrapper and use vanilla unpatched eigen, and you're going to get all the speed while mixing and matching units safely to your heart's content. The current status of this is that we have done the proof of concept implementation, and we're right now working on building up the production quality interfaces. By the way, if this sounds amazing and you want to learn more, there is a hot off the presses talk about exactly this, which just came out a couple months ago, and I highly recommend. So check it out. Here's the link if you are interested to learn more. All right, I'm going to shorten this section because the takeaway is easy to show, so we can have more time for questions at the end. When you're used to a units library, you are likely to be tempted to try making strong types in your serialized data as well. Then you're going to have a quantity meters length and a quantity meters instead of a double length and a double width. And doesn't that feel better? Well, there's actually a better alternative. So instead of this, just do this. Just stick a unit suffix on your field name. Easy. Clear, works out of the box. We can see what the schema looks like by the prototext in the left-hand and right-hand column. It becomes crisp, it becomes to the point, and there's no loss in unit safety. And looking at an example of other language code here, Python, we can see that they're both equally unit safe. It's just that it's the second example is just much more concise. So this is a good way to go for serializing and interfacing with other languages. Okay. Yep. That was definitely planned. The reason to use a units library is to make your interfaces easy to use correctly and hard to use incorrectly. You're still performing the same computations that you were before, but your intent is clearer, and your code is safer and easier to write, read, and maintain. To provide these benefits, a units library must strike an elusive balance. On the one hand, it has to minimize friction wherever possible. Burdensome code doesn't make you safer. It pushes people away from your library towards more error-prone alternatives. On the other hand, the library must know the common pitfalls and guard against them. We must make sure that wrong code looks wrong. A library that achieves this balance builds trust, which accelerates development. All that mental energy you spend tracking units by hand, double-checking your parameter passing, a units library can handle it, but more robustly. You can take all that energy and redeploy it more profitably elsewhere. What will you do with it?
So back in high school, they told me that radians are unitless. How do you handle this case?
Yep, this is a little bit, what's that? Oh yeah, repeat the question. So radians are commonly thought to be unitless. It was the question, and how do we handle this? I did slip some sly references to angles in there, because I couldn't resist. Yeah, it's a little bit painful for me because at the ATG library, I stood in the way of having strong types for angles. This was back when I was in thrall to the harmful fiction that angles are dimensionless, back when I didn't realize that it was a fiction, back when I was resigned to the harm. The gateway paper to check out here is a 2019 paper by Moore, Phillips, and Quincy called Angles Are Neither Intrinsically Dimensionless Nor Intrinsically Length Ratios. That's a good place to start. And then after that, there are two separate papers that came out in 2021 that make proposals on how to fix VSI. Now, this is a deep topic. It's a tricky topic. It's not as straightforward as I'm making it sound, but I have a lot of clarity now on this. And does that fully answer your question, or?
You give a one sentence. Angles are not unitless. Angles are for your library.
Oh, yeah, for my library, they are definitely, we consider angle as a recognized base dimension. In fact, this vector space representation of the unit magnitudes is what unlocks us from supporting exact symbolic reasoning about irrational real numbers. So we support radians and degrees out of the box for that.
One comment and a couple of questions. The other thing is in terms of benefits to users, the other benefit is same as doing your physics homework dimensional analysis, right? Like if you accidentally divide it instead of multiply or whatever, especially if you don't use auto, you will get a compound error instead of having to wait until unit testing, right? Maybe you are unit testing.
That's right, yeah. So the comment was that the Units library does more than I said. I did run out of time a little bit. It will also check your math, and especially, importantly, as you mentioned, if you name the type instead of using auto, then you're opting into that extra level of safety and checking.
And the other question is, when you're outputting a quantity of the unit, do you scale it up? Like if I do force times meter per second, will you output newtons, or will it be what the raw thing is?
Are you asking if I have a unit of a different magnitude?
No,
or?
I'm just saying as you're doing calculations, right? You're outputting a unit, right? But a unit can be composite, right? It's not like your base dimension. When you output it, you go up, okay, this is a newton. I don't just do kilogram meter divided by second.
Okay, so the question is, does the library distinguish between, say, newtons and an equivalent dimension unit, kilogram meter per second squared?
Just for output.
Just for output as in streaming output?
Streaming output. We'll do 5N instead of 5 kilogram, product, kilogram meter.
Yeah. Okay, so yeah, the answer to what we do for output there is if the unit is equivalent in dimension and magnitude to a known and named unit, then we're going to use the name instead of just the standard. But we will have a fallback. Right now, that was sort of a lower priority, so the output for non-named units is not really quite there. And that's fine because almost nobody in this room can find that out except I just spilled the beans. All right, so I saw a question here first. Mm-hmm. Mm-hmm.
How much of that would be able to sort of design against upfront versus after the fact? And what sort of strategies would you recommend for foreseeing this kind of design pitfalls?
So the question, as I understand it, was to what extent did we foresee the pitfalls that I mentioned ahead of time versus to what extent did we sort of run into them and have to fix them later? We benefited from this not being our first Units library, so we had a bit of a head start there. But these were all ones that came out in the review process of the initial MVP of the library. So having really good code reviewers is really important, I would say, to sort of double check people with different and varying perspectives to see things that I missed. And I think that helped us get these before we landed the initial version. I don't know if I would call that a general strategy, but I think it's probably part of one. Okay, question in the back?
Are you in communication with Mateusz Cooks, who's trying to standardize this?
Yes, I am. So We've been in communication with email. I'm really very impressed with his units library and the effort to standardize it. And right after CppCon, we're going to start figuring out how to start sharing some of the tech that we have here that, so for example, the vector space representation for magnitudes, we're going to start working on seeing if we can get that into MP units as well.
It seems like you have some really valuable experience with these lacking and vice versa.
I think that our experiences are quite complementary, and I think that I'm excited to work together so that in a couple of years when we have STID units, it's the best it can be.
What does it look like to add a new fundamental dimension?
To add a new fundamental dimension is what it would look like. Oh, I didn't repeat the previous question. So YouTube, the question was, have I been in contact with the author of MP units? Yes, I have. This question, what does it look like to add a new fundamental dimension? You would name the type, and you would create the type trait that gives the index for it in that ordering of base dimensions.
How do you avoid conflicts between two new fundamental dimensions?
Manually. So how do you avoid conflicts between two new fundamental dimensions? Manually. But it would be really cool if we could read the name of a type and then we could just sort them alphabetically and that would be done. So I think we are at time. There's a sign. I can see the writing on the wall or on the sign. Thank you so much for coming. It means a great deal to me. It was really a delight to come share this with you all.